Well, today we have a very, very special guest with us. Special in that he is Blaine Brownell, Fellow of the American Institute of Architects and a lead AP. He's a professor and director of the University of North Carolina at Charlotte School of Architecture. But the reason he's really special is because he was one of our first 40 under 40s for building design and construction, the class of 2006. So you were in grammar school then, right, Blaine? Well, welcome to the weekly, Blaine. Blaine and I are gonna have a chat about his work. Blaine is a kind of an expert, world-class expert in materials and systems for building products and building design. Author of 4 books about transmaterials. Terrific stuff on this innovative area of materials. And we're going to talk about some new things that Blaine is seeing out there that have an impact and benefit on the environment and on people's health. So we're going to talk about several of these, starting off with something called Biomimetic Surfaces. So Blaine, you've come across a product in this area. Can we talk about Eredal?
Absolutely, Rob. And thank you so much for having me. It's been a pleasure being in touch with you all these years. Hasn't been too many years, but so we'll jump into Eredal. So this is essentially a non-toxic silicon dioxide coating that's used as an antiviral ingredient. So why is this important today? And why, as you asked, Rob, about new materials and coatings, am I interested in something like Eredal? This past year obviously has changed. It's been a game changer, right? Mm-hmm. It's changed how we work, how we live, how we function in spaces, how we think about surfaces. And I think never before have we been so cognizant of disinfecting our surfaces, right? Thinking about COVID. The problem is that a lot of traditional chemical approaches to disinfecting surfaces and antimicrobial surfaces can lead to superbugs, meaning they can cause resistance and microbes to antibiotics. And we don't want that, because that creates a bigger health concern for humans. So biomimetic approaches look at there are ways to modify the natural surface nanogeometry of in a coating with something like silicon dioxide. So it's as if it's tiny particles of glass that, based on their shape, disrupt microbes' ability to propagate and to be viable on a surface. So this non-toxic coating, made in Germany, originally developed for air travel applications, but now available for a wide variety of programs, is dermatologically safe. It disrupts microbes' ability to be viable and to survive on a surface, but it won't cause antibiotic resistance.
Yeah, and this comes out of a company in Ahrensburg, Germany. They say it's liquid guard technology, and it's actually a spray that creates kind of a glass surface. It's a silica surface on there. So that's kind of interesting. Let's turn to another one, far UV lighting. Now, we've heard a lot about UV lighting supposedly killing microbes and supposedly killing, COVID virus, and there's some question about that. And you've come across one product called the Christie Counteract lamp from a company based out of Cypress, California. Could you tell us about far UV lighting?
Absolutely, Rob. So ultraviolet lighting is known, especially far UV, is known to have effective germicide capabilities, and has been developed in a kind of industrial capacity, industrial strength for hospitals, clinics, other areas where we really need an effective germicide. The problem is that ultraviolet light can cause, as we're familiar with, sunbathing too long can cause damage to human tissues. So even far UV can do that. This counteract lamp is based on a technology that's specially tuned. It's 220 some nanometers, a very particular band of UVC lighting, which kills pathogens without causing harm to people. And this is critical because just like with surfaces, we're very cognizant of the transmission of COVID in spaces, environments that we occupy a lot of the time.
Well, that's the main
right?
main transmission mechanism is through the air. So I understand they call this the CARE 222 technology from this company, and supposedly useful in like a movie theater or a museum, or a larger space would be a good possible application for this.
Yeah, absolutely, Rob. And it'll be really fascinating to think about lighting in new ways. Once we can have this kind of multifunctional light that keeps us safe while also providing illumination, it'll be an interesting kind of new way to conceptualize light.
Now, something you've written about in your Transmaterials books is shape memory alloys. Kind of a smart material, stuff that materials that do something when you apply either energy or heat or light or something to them. Yeah, and there's something called the air flower or the air flower from Lift Architects out of Greenville, South Carolina, that you've written about. Tell us about the air flower. What does it do?
Yeah, well, Rob, what intrigues me about this really ingenious application is that it ventilates without energy, without electricity, based on shape memory alloys' ability to manipulate surfaces in a tiny way with a large effect. So the architect, Lift Architects, devised what is essentially a kind of ventilated wall out of small modules with very lightweight panels that open and close, kind of like a camera lens. And these are all attached by shape memory alloy. And the idea is that, or their concept is that the shape memory alloy will change shape once the temperature rises above a certain point and within a certain band. And so once the temperature rises sufficiently to require fresh air intake, or wants you to have a little bit more fresh air, the system will all open, almost like flower petals.
Yeah. I mean, it's a biomimetic concept as well, isn't it? I mean, based on seeing flowers open and close and so forth. Yeah. All right.
Absolutely.
Another concept that you've talked about is rapidly deployable acoustic systems. There's something called the chat pod out of Lucerne, Switzerland, and it's a room in a room. Gensler was doing something like this. I know they have a kind of a phone boothy thing way before COVID, but this is kind of interesting because of how it's made, isn't it? It's
absolutely.
Recyclable and so forth. Yeah.
Yeah, I think with our new Zoom world, we're spending so much time in conversations like these. I can only imagine that during COVID, and especially after COVID, once we begin to reoccupy workplaces in a significant way, we're going to be sort of potentially in conflict with each other. Lots of buzz in the office beyond the kind of standard phone call. And so I think the chat pod made by Impact Acoustic and others like Gensler who are creating acoustic solutions, that's going to be really important to helping us readjust, if you will, to this new online and kind of hybrid format. And I would say too, Impact Acoustic also has others and others like them have other interesting solutions like sound absorbing light fixtures or suspended room dividers that also have acoustic properties. So I think the idea is that acoustic systems there's a huge potential for creative, interesting ways to approach acoustics that are very rapidly deployable and adaptable.
Yeah, the Impact Acoustic people make a big point that this is, 100% recyclable. They make it out of sawdust and tires and recycled content and so forth. So that's kind of cool. Very, very European, isn't it? Okay, our last example is one that's very close to you because it's research that's being done at the University of North Carolina at Charlotte by your colleague. So tell us about what Kyung-hee Kim, your colleague, is doing on microalgae facade technology.
Thanks, Rob. And thanks for the opportunity to brag about Kyung-hee a little bit. Professor Kim and others in the lab that she runs,
the integrated design research lab, right? Yeah. Mm-hmm.
Yeah, research lab is, and for me, if I could talk a little bit about the lab, it fascinates me as a model that I've long hoped to achieve, and they achieved it before I came to UNC Charlotte, which is a marriage. It's a really creative marriage between a kind of traditional design studio atelier type environment and a scientific wet lab environment. And so this lab has both of those elements. You can tell it's sort of a mashup between an architecture firm and a science lab.
Okay.
And
cool.
they have tanks with algae flowing, and they're designing really innovative, clearly architect designed facade systems. And so they've got
this microalgae window. Tell us about that.
Absolutely. So the idea, when I think we first heard about this notion of putting microalgae inside of a facade, I think it probably was a head-turning idea. What? You're putting algae in a window? Why would you do that?
Sounds like bold.
Yeah, it does. Why would we ever do that? There were some early prototypes developed by Splitterwork Architects and Arup engineering firm. There's one in Hamburg, a prototype a few years ago, as kind of a one-off, a not commercialized approach at that point. But for several reasons. One is that microalgae, as they mature and grow, the window naturally tints, right, where you have the most intense sunlight. So you have a kind of natural response that mitigates solar heat gain and a kind of solar shading.
Okay.
There's also the capacity for thermal insulation and also sequestering carbon. And then at the end, once you kind of cycle off the mature algae, you can use them as a biofuel. They can also be a food substance, medicines, et cetera. So it's a living agent that's used essentially as part of the design, part of the architecture.
And your colleague has gotten several research grants from the government and elsewhere to pursue this. So this is serious research. I mean, this is not some far-fetched idea. Mm-hmm.
Yeah, what really impresses me about what Kyung-hee and her colleagues are doing is she's taking this idea that was a little bit of a fringe kind of conceptual idea and making it a commercializable approach. So she's working with, she's partnering with architects and other industry organizations to figure out how can we make this a commercialized window, especially tuned to adaptive reuse of low-performing commercial windows of 1980s and earlier office buildings.
All those dreadful office buildings that were built in the late 70s and early 80s that are just energy hogs and so forth. So yeah, how can we do something about all that glass? Yeah,
that's right. Yeah. That's right. And it's a system that's it's kind of a package system, so it doesn't require retrofitting the entire glazing system that's there. It's easily installable. And we have a prototype that she's installed right now in our School of Architecture that she's testing.
Great. Well, this has been a fascinating conversation, as it always is with you. And we're delighted to have Blaine Brownell, professor and director of the University of North Carolina at Charlotte School of Architecture, with us today. Great to see you again, and keep up the good work at UNCC.
Thank you so much, Rob. And same to you at Building Design and Construction. I've always been an inspiration to me, and and everyone stay safe out there.
Thank you, Blaine. Take care.
Thanks, Rob.